Alrighty, everyone. Hope everyone is doing well. And we will get going in just a few minutes. We do have a sponsor, Goldman Sachs. They sent us some audio. Unfortunately, I didn't get it in enough time to get everything set up so that I can add it in here. So we'll have to do that next month. But I will get that all set up. How's everyone doing tonight? All right. So here's what our program looks like for tonight. We have Tim Berglund with us, and he is going to be talking about Kafka and being ACID as far as transactions go. Whatnot. We would like to thank our sponsors, Tech Systems, ShareWorks, Morgan Stanley, basically, Goldman Sachs, Lucid, STG, SoFi, Fidelity, Master Control, Novist, O'Neill, and I think that does it. Is there one? Oh, JFrog. Right, JFrog. And of course, I said Goldman had something for us. I'm not able to play it on the stream currently, but that's okay. Tim's trolling me over here, which is great. I would like to shout out that we are also streaming this out to YouTube as well. So you can find us just by looking up Utah Java or UJug on YouTube. You can find it there. And we're going to be posting videos there as well. So that should do it for us as far as that stuff goes. Other announcements that we have, the upcoming schedule. So we have Daniel Hinojosa talking about generics. I know it's been something in the JVM for a long time, but a little reminder, never hurt anyone. Plus there's always little things here and there that you forget about. So he'll be giving us a little update and probably some things you may or may not have remembered or known about generics before. In August, we have Mark Richards. His talk is TBD, but we will get that up as quickly as possible. And then in September, we have Daniel Shuda thinking architecturally. August and September, we're not quite sure if those are going to be online or not. That all depends on what's going on, here in Utah as far as COVID-19 and Lucid Works allowing other people in the building and whatnot. But we will keep you informed as we get more information on that. Announcements. Like we did for the last couple of months, we will be doing a Utah Food Bank donation in lieu of doing pizza so that we can help those that are less fortunate be able to get the food that they need. And door prizes, as always, we have 2 JetBrains licenses that we are raffling off. 1-year Agile Learner subscription for Venkat Subramanian's online website, his videos that are available there. And that is all we have as far as door prizes go. I don't see any questions. If people have questions, feel free to ask them here in chat. I will move them over to the ask a question thing, and then it's up to Tim as far as when he's going to be able to get those answered, and I will do my best to mark those as answered as they come up. So without any further ado, let's bring Tim on board.
Do it. Can you hear me?
We can.
Excellent. I think you can see me too?
Yes.
Well, that is good news. Now, yes, as for questions, Jason, could I ask you to keep an eye on that and ask them in audio when they come up?
Yep, I will.
Okay.
I will do that for sure.
That would be delightful. Now, let's just let the fun begin. My daughter's wedding from last December. And here we are. I want to talk to you tonight about some things you can do with Kafka that are really more architectural in nature.
Tim,
now,
do you want to go side by side currently, or just the screen?
You mean side by side with me?
Yeah. So we've got you on the left and then your screen on the right.
Probably the screen is more important. I mean, there's a camera on me, but let's go just that screen.
Okay, sure thing.
Yeah. Right, and we'll go back to faces when we're saying our goodbyes 90-ish minutes from now. So anyway, everybody, thanks for being here tonight. Want to talk about some things we could do with Kafka architecturally. Now, if you're not familiar with Kafka, this talk does contain a brief embedded introduction. Basically, I'm going to lay out the problem as I see it. I'm going to teach you just enough Kafka to solve the problem. Then I'm going to apply those things that we've learned about Kafka to the problems that we saw in the beginning. And those problems are all going to be ordinary things that happen in the distributed systems that we are building these days. We're kind of all distributed systems developers. All of a sudden, it snuck up on us. Like you didn't think you were. And then you realize, oh, wait, yeah, no, I completely am. That's just my life. Everybody always told me that was a bad life choice, but here I am, just kind of like the boiling frog. I have become one. And Kafka does some interesting things for you beyond just being a dang message queue, right? That's a terrible, very 2012 way of thinking about Kafka. There's a lot more interesting things we can do. These ideas are originally this guy's. That's Martin Kleppmann, and his book Designing Data-Intensive Applications is a great, really distributed data architecture guide. He is a leading authority on Kafka and event-driven systems. A lot of the best ideas that I see in event-driven systems come from Martin. I don't always know they do. Sometimes, like I think they were originated by someone else, and then I find out, oh no, that guy got it from Martin. So he's an important guy to follow, and his ideas on this topic have inspired this talk. But I like to start by thinking not about messaging, but about data, and really asking just what a database is. And this is kind of like the question, what's a chair? The undergraduate philosophy class question. The teacher will say, what's a chair? And everybody starts to try to define a chair, and you realize after a few minutes you have no earthly idea what a chair is. You cannot come up with the necessary and sufficient conditions that describe all things that you think are chairs and exclude all things that you don't think are chairs. It's really hard. It's hard to do that with databases too. Like what one is, but if you really tried to define it, could you? So you probably start with something like, well, it's a program that remembers things. All right, fair enough. It is that. But a file system is a program that remembers things, and most people don't think of file systems as databases. That'd be a little cutesy. So okay, maybe the database has some kind of data model. I mean, a file system is hierarchical, but files could be anything. It's really unstructured, but so maybe a database has some data model that it requires you to conform to. Okay, all right, that's something. I would like to be artificially restrictive, and I'd like to say a database is a program that remembers things and has a data model and has ACID transactional properties. Now, we all know that that's not true. Nobody outside of my rhetorical purposes in saying this for this presentation, nobody would agree to this. There are things that you think are a database, and we all agree are a database, that don't have ACID transactional properties, and that's fine. But work with me here. I want to try to make my definition a little tighter than it needs to be. To do that, though, I think we have to ask this question. Now, I think, and I want to, at a conference sometime, I want to try kind of like a game of distributed systems Family Feud, where you survey a bunch of people with questions like what is ACID, and then have teams guess the answers. Sounds fun to me. I'll do it someday. Probably everybody here would get the words right. You probably know ACID stands for atomicity, consistency, isolation, and durability. If you don't, the good news is you do now. But that's not much, knowing what those things mean. We tend, if you peel a layer back and try to give an account of what each one of these things mean, they get confusing. So I want to just give you a quick overview of what I mean by these words, not in the classical database sense, but how I want to talk about how these properties apply to distributed data systems and the distributed systems that we are building that are commonplace to build these days. And just to clarify there, if you're building microservices, then you are a distributed systems developer. You're already in that world. So if you're there, then these things apply to you, whether you think of yourself as a distributed systems developer or not. All right, let's start with durability. In the olden days, when I was being born, like in the 70s, what this meant was the transaction log gets written to tape. That was the first kind of durable database. It was a thing kept in memory, but we would take the transaction log and spool it off to tape. So if something went wrong, we could pull those transactions back in and have our state back. Pretty quickly, hard disks entered the world for very, very high-end systems. And when most of us came of age as developers, you probably still have this image in your mind. When I say durability, what that means is stuff gets written to disk. Now, most of our disks that we use these days don't look like this anymore. They are increasingly solid state devices and not super flat spinning metal disks with very thin layers of rust on them. But most of us, if I just ask you what durable means, you'd probably say it means, stuff gets written to disk. What's interesting is what a moving target this is. It used to be tape, then it was disk. Increasingly, for a distributed data system to have any kind of credibility, there needs to be some kind of replication story. Kafka, of course, has that. We'll talk a little bit about how it works. But anyway, durability is not super hard to satisfy. It's just interesting that it seems to, the goalpost seems to get moved on us over time. And our requirements get a little bit more stringent. Let's talk about atomicity. Now, this word gets overloaded in our world. Like if you look at, say, a concurrent collections library, you might have an atomic list mutation operation or something like that, where there can be a single shared data structure that's being accessed by multiple threads, and you have some semantics by which you can mutate that list where those two threads won't interfere with each other in unpredictable ways. That's not the atomicity I mean. What I mean in a database is really this goes to how the database handles faults, like crashes, power failures, and things like that. Let me just give you an example of how this really comes to us in the classical data sense. All right, usually we have, if you think of a database transaction in the undergraduate computer science textbook way, you've got this, and you begin some transactional context, and then make a write to a table, to some row in a table, and then make a write to some other row in the table, or maybe even another table entirely. But you just do a bunch of mutations, and then you commit those. And what happens is the database agrees with you either to do all of them or none of them. And so if there's any failure in the middle there, it has some mechanism to roll back the changes that it's made such that nobody ever sees them. And that's probably what comes to mind when I say atomicity or doing atomic writes. But let me propose to you something different. Again, ordinary garden variety 2020 distributed system. You've got some application, some service, and events impinge on that service. It receives input from somewhere, whatever that is. Maybe it's a Kafka topic, maybe it's a form or a React front end posting a blob of JSON to some endpoint. Some event hits that application. It does some computation, and it wants to remember the result. What does it do? Well, we're not animals, so we're going to write that result to a relational database local to the service. But maybe that's good enough. Maybe that's not good enough. Maybe you also have some distributed graph database you want to write that to, because you're running a recommendation algorithm, and those don't work very well in relational schemas. So you write it to the relational database, you write it to graph database, and you want to also be able to search on that, so you write it to an index in Elastic. That's fine, right? There's nothing weird about this. There's absolutely nothing pathological about it. You just have multiple writes that you want to do because there are these three interestingly different ways of reading the data that you've computed. The problem is, though, that you have that one application doing multiple writes, and so when something goes down, like if Elastic goes down, for example, which is a terrible thing if it did, then what do? The write failed. There was an exception on that write. Do you have to go back and roll back the previous two writes? Do you put it somewhere, write it to a file, and then come back and read that file later and update the index when Elastic is available? Like, it's a whole lot of responsibility you're putting on the application to deal with those multiple writes. That's a problem. You want all of them to work or none of them to work. I'm not telling you how to fix that yet. I just want you to see that's the atomicity problem in an example of the atomicity problem in the distributed systems we write these days. So we're going to have to fix that. That database example, where I was updating the two accounts, we don't really have to fix that. We have databases that do that. They're great at that. But now we've kind of gone up a level from those databases, and we need to fix this problem. All right, let's talk about isolation. Isolation is really interesting in databases. The textbook definition, and I think the winning answer in distributed systems Family Feud would be some description of what we call the serializable isolation level. Now, this is actual transactional isolation is typically configurable in databases that support this, and serializable is the most stringent kind of transaction isolation and also the least performant kind. We don't always even ever use it in production, but it's the thing we think of. Database transaction isolation levels are, they differ in vendor-specific ways, in interesting ways. It's one of those things where you really have to go deep into a database to understand them. But again, to a first-order approximation, we just think of serializable isolation, which means what we want is to be able to issue multiple writes to our database from multiple actors, multiple threads, multiple processes, multiple containers, and we want it to look like those were issued in a particular order in a single thread and always run in that order. That's what we want. Let me show you why this is hard. So garden variety distributed system, we have a single shared mutable update in place data store. You know it as, say, Postgres, and that's a great thing. You've got Postgres maybe fronted by some service. Maybe these processes can access it directly, but these are individual services or instances of a service that are trying to, my example here is create a user account. So maybe somebody coming in through the website, React front end, tickles the process and asks for a new user. Somebody's coming into the mobile app. That mobile app calls the API on process 2, and there you go. So process 1 gets a request and needs to know, I'm typing in on my little form on my web app, I'm saying, hey, I want to create an account for Tim, and process 1 needs to know, is there a Tim? And there's not one. Well, kind of at the same time, I guess it's interpreted as being just after that. Process 2 asks the same question. And so now we've got this state local to those two processes where they both think there's no such thing as a Tim. And so process 1 is going to ask for a Tim. Process 2 is going to ask for a Tim. And that's bad, right? Because we don't want to create two Tims. You probably wouldn't fall for this. Most of you are smart enough to know not to actually write this bug. A lot of us, in the Atomicity example, a lot of us would fall for that and think, oh no, I need to write a bunch of framework to deal with these multiple writes. This one, like you do something to avoid doing this, but this illustrates the problem. When you've got a single update in place data store and multiple processes for contending to access to the same place in that data store, then isolation is a problem. And this is the distributed isolation problem, not the conventional transaction isolation problem that relational databases already solve really, really well. When we're building systems like this, you need to do something different to avoid this problem. Consistency, I've always felt like consistency is like the least favored letter of acid. Like, we wanted it to sound cool and dangerous, and aid, which is acid without the C, just didn't sound cool enough. And so we had to put consistency in there. But it is important. What it means is that after we're done mutating the system is not going to let us leave it in a state we don't like. Now, that's usually, the textbook definition is usually given with the word inconsistent. We're not allowed to leave the system in an inconsistent state. I find that unhelpful. It sounds like, well, writing doesn't mess everything up. And you think, well, of course writing wouldn't mess everything up. Why would writing mess everything up? It's like saying the system doesn't have any bugs. I mean, obviously we're not going to design bugs into it. But I think a better word to use here is the word invariance. So for the system to have the property of consistency, that means there are invariants it will enforce. Like I can't create the same user account twice, or I can't make an account balance negative or 0 or something like that. Whatever they are, they're these business rules, and the system requires that those be enforced, and you're not allowed to mutate it in a way that does not enforce those invariants. So there are some problems. It looked like durability seemed simple. Consistency is a little weird. Isolation and atomicity seem pretty complicated, and they seem hard to solve at scale in a distributed system. So let's take a break for a second, now that those problems are on the table, and look at what Kafka is. I want to give you a quick, maybe 25-minute overview of the whole ecosystem. Kafka, a lot of people think of Kafka as a scalable messaging system. I think a better term to describe it is an event streaming platform. And it's got increasingly all the components you need that you would have had to build on your own to build event-driven reactive systems. Let me take things one at a time. Starts with topics. Now, a topic is a term that occurs in messaging systems, which I think Kafka is properly not, but it borrows this term from messaging systems. And events topics are things that store events. An event in Kafka is just a key value pair. And when you put an event into Kafka, you put it into a topic. And that topic stores that event in an ordered way. Now, what's important about that storage there is that it really is storage. This is not some ephemeral buffer to hold things around for a little while till someone can get around to reading them. This is actually a log. It's a log on disk. It's durable, stored on disk like any other file, replicated. Talk about replication in a minute, but it's as durable as any database you've used. Kafka will allow messages to expire from the log, but that's configurable. So if you, I was running a test a couple weeks ago where we had a 15-minute retention period on a topic because we were writing like almost 3 gigabytes per second to the log, and that's crazy, right? So we didn't want to keep too much data around. So we set a really short retention period, but you could have an infinite retention period also. This is durable data. These are logs. So what's the topic? Log of events. They're ordered. Reads and writes are very, very predictable in the amount of time that it takes a broker to do them. And because it's a log, I need to underscore the fact that these are persistent things on disk. That means you can actually store the history of your system in a topic. Now, it'd be no fun if topics were just a single log on a single machine, right? We call those machines brokers in Kafka. And increasingly, when people are more and more running Kafka in the cloud, and the idea of an individual broker is becoming a little old-fashioned, right? There's always a Kafka broker, but the abstraction that a cloud service presents to you shouldn't be you have 15 brokers. It's more and more, and you're using Kafka in the cloud. You're just thinking about topics. But to make those topics scale, like that test I ran the other day where I wanted 3 gigabytes per second, it was actually 2.7. So don't sue me, but it was a lot of data. Like one broker is not going to do that. There is no one Kubernetes container running on one cloud instance that's going to make that happen. That has to get split among a lot of machines. So partitioning does that, splits the log up into pieces, calls them partitions, and allows us to assign those partitions to independent nodes in the actual cluster. Like maybe your cloud service abstracts that away, but at some point, there's a machine that's storing data on disk and managing that partition. So what happens now is we have a key value pair. We want to write it, and we hash the key. We run the key through a hash function, and that hash function, mod the number of partitions, tells us what partition to write the key to. And the same key over and over again will always land in the same partition. So that key is not a unique key that identifies the event uniquely, but it's usually the identifier of some entity in our system. Like it's the thermostat that's producing the temperature report, or it's the piece of manufacturing equipment that is reporting the sensor reading, or it's the smart car that's phoning home, or it's an order. A microservice is processing an order. This is an order ID or a user ID or something like that. So all those same keys always end up in the same partition, always in order. Partitioning causes you to lose global ordering, but still gives you the guarantee that the same key is always going to land in the same order in a partition. All right. Once again, these provide scalable writes, scalable storage, scalable consumption. We'll talk about storage in a minute, but this is just a way of taking that log and spreading it out among lots of machines. Ordering is within partition only, but is strict within partition. And picking your key becomes super interesting. right? That's the thing that gives you ordering. So you spend a lot of time thinking about that. Take a quick breath here and see if there's any questions anybody's got. I'd be happy to take those.
We do not have any questions at this time.
Love it.
There was a little hiccup in the stream. Some people were saying that they missed some, although exactly where that happened, I'm not sure because I was connected the whole time. So
Okay.
I'm not quite sure where people were talking. If you want to say in the chat, then we can go back and take a look at that if you would like. Or once again, I posted the link in YouTube. You can catch the rewind on YouTube as well.
Got it. I will, if those questions come up in a specific way, I'll wait for you to bring them to me.
Okay. Yeah, right. I'll let you know.
Cool. Okay. Let's talk about replication. Now, this is showing the actual physical brokers here. Those 4 big boxes. Those are individual machines, or whatever that means, right? Containers, instances of the Kafka process. They're independent brokers. And we take that one topic and we're going to also split it into 4 partitions. There doesn't need to be a relationship between the partition count and the number of brokers at all. There's nothing that fixes those to be the same thing. It just makes the slide pretty. So, I could have 50 partitions, I could have 100, I could have 3, doesn't matter. What we do though is, instead of just having one copy of each partition, we're going to make multiple copies. So there you see 2 follower partitions on brokers 2 and 3, and 1 leader. We'll do the same thing for partition 2, partition 3, partition 4. So those each partition has a leader and 2 followers. And the way it works is when you're writing or reading, like there's a client application that's writing or reading, we're going to look at those next, you always talk to the leader. And well, asterisk on always, there are some potential complicating factors there. But for now, we're just getting to know Kafka. Just think of it as you write to the leader, you read from the leader. It's very simple. And the followers are responsible for going out and getting those new messages that get written and replicating them to themselves. So they're constantly working to stay up with the leader. They're always going to be behind by a little bit, but as long as they're close enough, then they're considered to be in sync and valid replicas. If one of them goes away, either becomes non-responsive or drops too far behind the leader, like say broker 4 burns up, then we elect a new leader from the remaining in sync replicas. And that happens automatically. Consumers will be identified, producers will be identified, the clients learn who the new leader is, and you go from there. So that's just happening behind the scenes. From the development and architect perspective, you're not thinking about this a whole lot, happily. Okay. Producers. Producer is the client application that writes to Kafka. So this is code you write. The producer is code you write. And you declare a dependency on a library. The Java library is the native one that comes with Apache Kafka. There are dozens of others. Some of them are supported. Some of them are just out there in the open source world with still people happily using them. But that's what the producer does. It handles all the plumbing and the network connections and the connection pooling and the figuring out what partition to write to based on the key. All the smarts happen in the producer. It's actually, there's some pretty sophisticated code in there, but
we do have a question here, Tim.
Yes, please.
All right, so this question comes from Sean, and he says, is there a best practice for cold storage of older events when the amount of data becomes too large for the brokers to store?
Ooh, well, there are a few things. Number one, there's a KIP in Kafka. KIP is what you call, KIP stands for Kafka Improvement Proposal, to build in tiered storage into Kafka. And so there isn't a best practice so much, but this is a future feature of open source Kafka where you'll be able to configure it with your S3 account details. And after a certain age, it'll take messages and spool them off to S3 and let them live out there. This has been announced. No, that KIP is certainly there. that's all I can really say. That's I think it's KIP 405. Definitely pay attention. And I always hesitant to talk about commercial things, but cloud services, it always seems to be okay to talk about cloud services. Pay attention to the Confluent blog, this summer. There could be other things that we talk about related to KIP 405. That's always possible, right? But that's clearly essential. And this talk isn't really the database inside out Kafka architecture talk, but once you get into that mindset, if you just Google that phrase, you'll land on some good talks and articles. Database inside out Kafka. It becomes clear that you ought to store a lot of data in topics. And so that cold storage or tiered storage becomes important. And that's the thing that's actively under development. And there's likely to be interesting news in the next few months.
Perfect. Thanks.
Yep, you got it. All right. Producer puts messages into topics. It sounds so simple, but again, it's not. There's a lot of code in there that you never want to write. Java is the native one that comes with Apache Kafka. Go, .NET, C, C++, Python. Those are all freely available and also available in supported modes. Confluent offers a supported version of those. So those are kind of like the more mature languages. But everything else, I mean, there's a very mature JavaScript library. There are multiple other Go options, at least one other Go option, several Ruby libraries. So whatever your pleasure, you can find it. But really, languages of the JVM have pride of place here because the Java library is always first. And if your language has any sort of Java interop at all, which it probably does, it's Kotlin or Scala or Groovy or Clojure, you can find a good wrapper for the Java library and really not have to worry about that too much. All right, consumers. Now, it is better to give than to receive, but it's a lot more complicated to read than write. So let's see how that works. Here is our partitioned topic and a single instance of a single consumer. So all three of those partitions, those messages are going to land in that consumer. Now, consumers are single-threaded, fundamentally single-threaded things. There's no such thing as a thread-safe consumer. All you can do is make a thread pool and multiple instances of your consumer and run them in threads by themselves. Each consumer is a single-threaded thing. And they will, that one consumer will receive messages from each partition. And you don't know, so in a given partition, again, you have a strict ordering guarantee, but you can't really predict whether you're going to get a message from 0, 1, or 2 next, right? They'll just land there. You'll get them in order by key, and that's good enough. However, when you consume, you don't really consume. So I can have two consumers reading from a single topic. I can have hundreds of consumers reading from a single topic, each maintaining their own offset in that topic. So they can be reading from a different place and in various stages of caught upness, and that's fine. There are huge implications here. What this means is, and somebody asked about tiered storage before, this means I can have a lot of data hanging around in this log. I can have the whole history of my system. And that allows me to create new applications in the future that that process that data in newly valuable ways that I haven't thought of yet. So usually when I'm making a topic, I'm thinking of how I'm going to read it and what I'm going to do with it when I read it. Somebody else might think of something else to do with that data when they read it. That's fine. They can write consumer C or D or X or E, Q, or however many you have, as many consumers as you want. You can build them. Also, you can scale consumers. So I've got consumer A and one instance there, but what if message traffic picks up and consumer A can't keep up? Well, I just deploy another instance of consumer A. The consumer group is what it's called, automatically negotiates with the cluster to get a fair assignment of partitions. So the fairest you could do here will be 2 to one of those instances and 1 to the other. But if I deploy a third consumer, they'll shuffle around again, and it'll just be 1 partition per consumer. So I've got horizontal scalability in the consumer group basically for free. You don't really do anything to make that happen. Now, one little wrinkle about that is if my consumer has state, like say I'm computing a sum over a window, what's the total of the transactions, financial transactions that happen in the last 5 minutes? That's fundamentally stateful, right? I have to keep a list of them and run a reducing function, sum function over those. So I have to have that stuff in memory. When we go from here to here to here, the consumer API does not help me with that state. It does nothing to help me with that state. I'm going to have to build that framework. So hold that thought. We're going to talk about that in a minute. All right, consumers, client application. All they do is read messages from topics. The API is very simple. You say, hey, I wish to subscribe to this topic, and you wait, and then it gives you a little bundle of key value pairs back when messages show up, and that's all it does. It does give you horizontal elastic scalability. If you're stateless, you have to worry about state yourself, and all the same languages as the producer. Pretty cool so far. Going to take another quick breather, see if any questions are popping up. All right. If this was all we had, or all you knew about, you'd go off, you'd get to work, you'd build things, and you'd start bumping into patterns. Like you'd see, wow, there's data that's not in Kafka, and I'd like that data to be in Kafka, of course. And you'd say, well, I need to write a little program. I got something in a relational database, and every time a new record is inserted, I need that to be produced as an event in a Kafka topic. So, okay, write a little program to pull that table and look for a new ID number that's higher than the last one. And when I see it, I'll produce that record to a Kafka topic. Like, okay, that's good. I can do that. And then like a week later, it'd say, oh no, there's this other table, but I also have to look for updates, and that's cool. So I'll check on a timestamp field and for a new ID, and I'll just build a little new version of that service and have it run. And then you're like, oh, well, I need to write some results into a relational database. Let me just make a little service that consumes the topic and writes things out to a table. And after a little while, you'd extract a framework from this, right? You'd be like, no, this is totally a framework. I like writing frameworks. Frameworks are fun because I'm in charge. There's no product owner. There's no business stakeholder. Nobody's telling me to do stupid things that make me write ugly special case code. I am the boss of frameworks. That's the temptation for every developer in a situation like this. I might even say not temptation, but trap. And you want to avoid this trap, right? You want to avoid writing undifferentiated code that does not directly serve customers or deliver value to the business. If you want to make an impact as a developer, you want to write code that serves somebody, that doesn't just solve a problem that only you have, because probably somebody else has solved that problem, and that's what Kafka Connect is. Kafka Connect is the first thing, so we're kind of out of the core cluster now. There's brokers.
Question, Tim.
Yes, sir.
You
Go
want to
ahead.
field one? Ron says, have you tried Amazon MSK with Lambda consumers?
I personally have not. Very good question, but no, I haven't. I've got some guys on my team who have messed with it, but I can't speak to it myself.
Alrighty. Thank you, Ron.
So getting outside of just the core topic, produce, consume kind of thing, Connect is the first thing that happened in the Kafka ecosystem where the community recognized, hey, we need some infrastructure. We need this thing to replace everybody's buggy partial implementation of a data integration framework. And that's what Connect is. So when you have Kafka as really the center of your world, the central nervous system of the data in your enterprise, that's where it wants to be. You've got all these kinds of applications connected to it. You got microservices integrating through it. You're pulling in changes from relational databases, writing results back out to databases, doing stream processing, doing search, all this kind of stuff. That's all great, but those arrows are the same. That's undifferentiated code. No matter who writes those, you do it, a competitor does it, somebody in an unrelated business does it. It's the same thing. And so it'd be nice if you could just get access to that code one time. That's what Connect is. Connect is those red arrows. Now it runs on its own infrastructure outside of the Kafka cluster. So you've got your your brokers, your topics in there. Connect runs on servers of its own. There are source connectors that pull data in from the outside, and sync connectors that push data back to the outside. Those source connectors are producers. The sync connectors are consumers, and that's all a connector is. Connector, there's a Connect API. That's a Java API. It's very simple. Just a few interfaces to implement, some annotations. It's not much to it. Connect is distributed, so I can have a cluster of Connect nodes that are all doing this work. If you've got like a big thing that you're reading in from, or 10 tables that all have the same kind of data in them, you might want to distribute that among multiple nodes. Or you're writing to S3 buckets, just a huge amount of data that one node could never keep up with. Well, again, Connect can cluster. Connect is declarative, so you just configure it with a little bit of JSON. You post this at a URL on the Connect server, and as long as that class you see on the third line there, that connector class, as long as that is class loadable, in other words, as long as the connector is installed in the cluster, which you can do with a command line utility or with however it is that you deploy software, then this connector will start up and begin running and begin doing its data integration work. So the idea is you want to keep from having to write any of that data integration code. Confluent maintains a hub of these things, and there's so many of them, and they are not all open source. I mean, this is open source, open or source available. Some of these are commercial. This is like everything we know of that we've curated and we're willing to say is a decent connector. And some of those, Oracle Golden Gate is on here, and that's I don't know if there's an opposite of free, but it is if there is one. But there's plenty of open source ones there too, and of course stuff on GitHub as well. You could probably find a connector for what you want. If you can't, if you have something that's really special purpose, but you still want to write a connector, again, the API is not going to be the hard part there. The hard part of a connector is usually interfacing with the external system. By the time you get to writing a connector, you probably know the producer and consumer APIs really well. And the Connect API itself is not a huge lift, but you have to talk to some system, and that ranges from trivial and pleasant to makes you want to consider other career options. So it just depends on what you're connecting to, how hard that is. All right, again, summarizing, Connect is a declarative data integration framework, all kinds of connectors. Hopefully you'll never have to write one. Horizontally scalable, the Connect cluster is a cluster. Nodes can die, and those integration tasks will be passed off to other nodes, and it's pretty easy to extend. The next thing Kafka gave us was a better way to do stream processing. People found that those consumers got complicated. You often want to do stateful things. It's stream processing. Often time windows matter, like what's the average temperature over the last hour? Well, that means like I have to keep some kind of state, either all the messages of the last hour or just my running average or something. I have to remember something. And once you start dealing with state, dealing with aggregates and interesting stream processing step-by-step topologies, a lot happens in there. A lot, but it tends to fall into just a few categories. If you think about what is it that people do in their consumers, I get to ask people this sometimes, like enterprise architects who are running big teams that are doing interesting things with Kafka. What do your consumers do? Well, one thing they do is they'll take entities in a topic. So there's a topic that has serialized versions of entities like user records or car descriptors, automobile descriptors, or something like that. And you want to take that data in that topic and turn it into something that you can do a lookup on, like turn it from a topic into a hash table, or as I say, turn a stream into a table. Streams can always become tables. Tables can always become streams. This is a thing that people do in their consumers. Joining, you might want to take some other stream, like say I've got a topic that's got descriptors of all my smart cars in my network, and I want to turn that into a lookup table. Okay, then I've got another topic that's got reports from a pollution sensor in that car, and I want to enhance that pollution sensor report or enrich it with information about the car itself? Well, I have to join, right? I have to take that event from the pollution sensor topic and join it to the table I created with the car data. We call that enrichment.
Question, Tim.
Yes.
About streams. This is from Sean George, and he says, "How does Kafka Streams handle late arriving data for time windows?"
So there's two kinds of late arriving data. Data that is late enough, not so late that we can't get to it, and then data that's so late that it's considered actually a fault. This is configurable, but let's say we'll keep a day's worth of windows around in the stream processor node. And so if a message arrives in the topic and the event time of the message indicates that it belongs in the previous window, or a window from an hour ago, or whatever, as long as we've got them lying around, then we'll go back and we'll update the results of that window, and produce new records to the output topic, whatever that entails. But after the window is closed, it's still perfectly fine for data to arrive, and we will. That's what it does. It goes back and updates the results for that window if the data arrives late. But there is only so much of that we can put up with. So it's possible. That's, again, these are all knobs you can set, and it's possible for that data to be too late and say, well, it was 6 months ago, man. Forget her. She's gone. It's too late.
Great. Alrighty. Thank you, Sean.
Yes, Sean. Thank you. Everybody who's asking questions, you're doing a great job. Okay, computing aggregates over streams. This is another thing you do all the time, right? I've given examples of averages and sums and other more sophisticated kinds of aggregates. Aggregation implies grouping. Grouping implies potentially large, clunky, in-memory hash table-like things, and that implies distributed state management in ways that sound like a pain. Even worse, stream-to-stream joins. That's even hard to think about. But imagine like you have 5 different user databases in your company, 5 different views of what a customer is, we'll say. Not that would ever happen, but maybe in your company, you just happen to have 5 separate customer databases. Well, I described earlier that change data capture process where when there are new or changed records or deleted records, I'll produce an event to a Kafka topic describing that change in that table. Well, imagine I did that change data capture on all 5 of those user records. And then I wanted to join those 5 streams together to have some kind of completed view of the user. Now, I understand if you've ever done master data management before, it's literally a cottage industry of its own. There are conferences about it. It's a complex topic, but conceptually, this is a good example of how to think about stream-to-stream joins. If I've got tables producing changes to topics and I want to join those streams together, then I can have a unified version of the user. We've got some other neat examples online of like orders and shipments. Those are both event streams, and you might want to join those streams and figure out what orders haven't shipped within your shipment SLA. That's a stream-to-stream join. And okay, you want to do all these things, and you want to scale in a container and cloud-native way these applications which are inherently stateful. All of that is a very tall order. All of that is a lot of framework code. It is the ultimate Admiral Akbar trap for you to try to build that on your own. This is what Kafka Streams does. Kafka Streams is nothing more than a functional Java API. It looks a lot like any functional collection framework that you've seen in the last 10 years. Lots of concepts in there that are familiar. There is a map method. There is a reduce method. We can't get rid of them. They're still there. But there are a lot of other higher level methods, like there's a group by and there's a join method. There are methods for writing intermediate results back out to Kafka topics. Lots of most sophisticated operations are one-liners, and that allows you to build very sophisticated stream processing topologies with a little bit of code. The 2 key data abstraction in streams are streams and tables. I kind of already described those to you. A stream is really just a topic. It's just events happening. And a table is a way of taking that stream and turning it into a lookable, upable thing, like a hash table. Also, the problem with state in the consumer API, Streams solves that for us. So it has this embedded state store that actually, it's like totally pluggable and swappable and everything, but out of the box, it's RocksDB. So all that state that your stream processing application is creating, it needs in memory, it needs on disk locally, and that is a RocksDB instance. So you get this very robust little embedded database. Also, those RocksDB state stores that are being created by your Streams application are persisted, a copy of them is persisted back into the Kafka cluster in an internal topic. So all that state that you've got in those nodes, in those Streams applications, is durable. It's on disk, locally on those nodes, and in topics back in the Kafka cluster. So if one of those goes away, we can migrate that state to a surviving node and keep working. So much more to say about it, but this is a platform overview. So I think you've got enough. Streams is a Java API. It's got all the usual suspects of filtering and joining and aggregating, all the things you'd need to do. Importantly, I didn't stress this yet, but it's a library. I mean, it's literally, you put it in your Gradle or your Maven build, and it's a jar, and it's dependencies that get pulled in. That is what Kafka Streams is. It's not like this extra cluster that you stand up. In fact, I'm just going to go back here. It's just your consumer. You write your application. Maybe this is a Spring Boot application that's managing some REST endpoints and doing some other kind of stuff, whatever life was before you started using Kafka, and then you add stream processing to it. That's a new thing that your application does. You don't stand up a special cluster to go run your stream processing job. It's just a consumer. However it is you deploy Java applications, that is how you deploy a Kafka Streams application. If you hot deploy WAR files into Tomcat, I hope life is okay for you. It's okay. Kafka Streams will work there. If when the tests pass on new commits that are merged into your main branch, then the CI/CD system automatically builds a new container and deploys it, and it's like living in space. That's fine too. Kafka Streams doesn't care. It doesn't care how sophisticated your deployments are. You don't run this on special infrastructure. It's just a JVM application. And totally horizontally scalable, kind of fulfilling the promise of consumer group scaling is you start getting it for real in Kafka Streams. All right, last in the platform overview is a language, CaseEqual, occasionally also called CaseEqual DB, the streaming database for event streaming applications. It looks just like SQL, but it does lots and lots of stream processing. So this is joining a stream to a table, grouping by a field, computing an aggregate on another field, and emitting the aggregate, two aggregates, and a field in the table to a new Kafka topic. So it's consuming from two topics, doing a bunch of computation, stateful computation, and then producing the results to a new topic. CaseEqual runs on infrastructure of its own. So Kafka Streams is a library that you use. To use CaseEqual, you stand up a server and you deploy the CaseEqual process to that server. It's got a REST endpoint. You throw your CaseEqual queries at that REST endpoint. When you want to query the state of a table that you create, like if I wanted to look up the average rating of a movie from that previous query that I showed you, then you'd throw that query at the REST endpoint as well, and you get back that value from that entry, that key in the table. So runs on this horizontally scalable server infrastructure. It's just an instance that you stand up. And again, this is it's a community thing. You go download it, build it, run it. But it's these queries are constantly consuming from their source topics and constantly producing to their destination topics. CaseEqual queries never stop. They're always running. To summarize, it's a declarative stream processing language. stream and table abstractions, just like Kafka Streams, filtering, joining, aggregating, just like Kafka Streams, run it on its own, horizontally scalable CaseEqual DB cluster. And I say just like Kafka Streams, as it happens to be made out of Kafka Streams. It is itself a Kafka Streams application, so it inherits all that functionality. That's really the Kafka platform overview. I want to start applying this stuff to the problems that we laid out at first. But again, I want to ask you, just take a breather. I'm going to take a sip of water. And if you had a question brewing, you can ask it. All right.
Oh, we do have a question that came in, and it is from Sean George. And Sean says, what would you choose KSQL over, when would you choose KSQL over Kafka Streams?
Good question. First of all, if I wasn't using a JVM language and it was hard to use Kafka Streams is a Java library. So if I'm not using Java, then I want to think about CaseEqual. Also, streams make sense when there's an application, right? When you've got a microservice that is consuming events from Kafka and needs to do some processing, or maybe there's like 4 topics it needs to join and do some grouping of, and then that creates its input, and it can do its work from that. Well, then you want Kafka Streams kind of on the bottom of that service, consuming the topics, doing the stream processing, and giving your service what it needs to do its work. So when the application has some other life that's not just stream processing and it's Java application, I find most of those teams fall into streams. Like they want to use streams. They take a few days and learn it, and they complain while they're learning it, and then they stop complaining forever, and it's beautiful. That's kind of how that goes. So when there's some other reason for the application to exist and it's Java, you probably want streams. If there is no other reason for the application to exist, like you just have some topics and you want to do some stream processing on them, and you want the results to go into another topic, or you just want a point queryable table in memory, well, that's perfect for CaseEqual DB. You stand up the server, you don't write an application. You just say, hey, I want a few containers of CaseEqual DB, and I'll throw my queries at it, and they will run. And I don't have to write anything other than the SQL code, the CaseEqual code. So you want to think of it that way. I will say CaseEqual DB is growing and adding features to the point where I feel like it's starting to compete with Kafka Streams a little more in a positive way. It's not, there isn't, it's all the same ecosystem, so there's not actually a competitive relationship. But I feel like the gap between what you can do in Streams and what you can do with CaseEqual DB is closing. It's never going to close all the way. Streams is always going to be more flexible. It's always going to be the go-to choice of the stream processing microservices developer. But in the margins, more and more of those cases are getting nibbled away. A more interesting question that I hope someone asks me is CaseEqual DB a database? But I'm not going to answer that until somebody asks it.
All right, well, until that one comes in, we have one from Bill Harton. And okay. Bill says, lots of servers of differing types will require lots of communication. How well does it, I'm assuming Kafka, or maybe it was Kafka Streams, how well does it perform for typical scenarios?
That unfortunately, it's difficult to answer generalized performance questions. I mean, people get Kafka to do amazing feats of performance at amazingly low latency, and it is horizontally scalable, and consumers are all horizontally scalable, and producers likewise. So you could generally get the scale that you need, but it again, the specific how well does it perform? That the answer to that is always contextual, right? There's a system of yours, and it's performing in a particular way in that system. I could give you benchmarks, but those benchmarks aren't going to be contextual. What matters is how your system performs, and people can make Kafka do very big things.
Alrighty, well, thank you, Bill and Sean. I don't see anything else coming in, so we'll get back to it.
All right. Let's take those problems that I laid out: durability, atomicity, isolation, consistency, and let's see how Kafka solves them. We know enough Kafka to solve them now, so let's just do it. All right, durability. Remember, Kafka stores partitions as logs on disk, and they're replicated. This is trivially satisfied. I think there's not much to say. Kafka is a durable system. Yes, topic data has a retention period, and yes, you can set that very short, but you can also set it very long. It's just up to you how long that data is going to stick around, and it can be infinity if you've got the disk space for it. So durability, check. It's a modern distributed piece of modern distributed data infrastructure, and it remembers data. Okay, atomicity. This was our problem that I wanted to focus on. Remember this? When one of those things dies, we're doing multiple writes. This is not a thing that friends let friends do. Doing multiple writes puts way too much responsibility on that application and causes you to have to solve the same problem over and over and over again when you've got actual valuable problems you could be solving for the business or for its customers. So here's what we're going to do. To the surprise of, I hope, no one. We're going to put a Kafka topic in there. So now what happens is the service, the application, has events happen to it. It receives input, it does computation on that input, and it produces the result to a topic. And that operation is atomic. Producing that one result is an atomic operation. If I have to produce multiple results to multiple messages to multiple topics, there's a transaction API that lets me do that atomically also. Definitely not covered tonight, but the point is, this is an atomic operation. And just to keep it simple, if I have that produced as a single message, it is trivially atomic. Those arrows down. Yes.
If you've got a minute. All right. This first one is coming from Jonathan Bronson, and Jonathan says, does Kafka support custom compaction/snapshotting policy for when a retention period ends, or does it always just keep the last known value for each key?
Got it. Okay, so no and yes and no, and sort of let me go over that. There's two kinds of compaction, or two policies there, and one is compaction, which is every so often, based on various configurable conditions, you're going to take old log segments and compact them into the smallest number of log segments possible for a partition, and only keep the most recent version of every key. But that's a special thing. That's a compacted topic, and topics are not compacted by default. Pardon me, sneeze coming up here. And I don't know where mute is on Crowdcast. Sorry.
Sorry, I should have had you covered. I didn't.
No problem. No problem. The normal seasonal allergy season for me is like weeks ago, but boy, this week is killing me. Okay. Those arrows on the bottom connecting to Elastic and a graph database and a relational database, what are those? Do you mind
another question?
I don't.
Alrighty. And this is coming from, and I'm sorry, I do horrible with Indian names. Prashanath Bachu says, can I dynamically, at runtime, create a consumer, consume some messages from topic A, and then connect to another topic in the same session?
No, consumers don't behave that way. A consumer has, well, there's a cluster it's connected to, and it could. No, that's okay. That's okay. I could subscribe to one topic, do some consuming, detect some condition that tells me I want to stop, and then subscribe to another topic and do some consuming from it. That is okay. That's not typical. Usually a consumer is like a function over events in a topic. But there's nothing stopping you from doing that. Any other questions?
Great. No, I do not have any other questions.
All right. So my question for you, and you can answer this in your mind, those arrows on the bottom, what are they? Those are Kafka Connect. So I don't have to write code. The code I write in my application is producing the dang message to the topic, and then I'm done. I get an event, I do stuff with it, I produce the output, and I stop worrying about it. I cannot wonder, is Elastic working? Is the relational database up? Is my recommendation engine working? You can't bother with any of that stuff. Now somebody has to, right? The observability of the system and the uptime is a concern for the business. So SREs care, but the application doesn't. The application produces its message and moves on its way. And those connectors, when there are new messages, will move along. They'll read the new message and they'll write it to their sink. And there are services that we don't see on this slide that are accessing Elastic, doing product recommendations, reading history out of the database, whatever they are. And so when Elastic goes down, again, to pick on it, we keep working. We don't know Elastic is down. We're just producing stuff to our topic. And those connectors keep moving forward. Of course, SREs are working busily to get Elastic back up. They do. The connector says, oh, good, you're back. I remember where I was. Let me get caught up. And it gets caught up. What we've done is we've solved that atomicity problem and taken all of that work out of the application code. There's one very simple thing the application does. And the application, this is key to reactive or event-driven event streaming software. You do your write and you don't worry about it. Like you consciously don't know what's going to happen with that. Again, somebody at some point absolutely knows what services are up and running, but that application does that right. There could be 3 new kinds of syncs that get added to this data. If it's very important data, it doesn't matter at all. The application doesn't need to worry. It does its atomic write and it moves on. All right, isolation is a little harder. This was our scenario where we've got multiple processes contending for access to a single update and place data store. And okay, nobody be surprised. That's right. I replaced that with a Kafka topic. This takes a little more explaining, though. I feel like the last one was well, it wasn't obvious until you've seen it, but this takes a little bit more explaining than the last one. So that topic is not users. We don't really know what a user is. This is requests for a user. So process 1 puts in a request, and by the way, it sends its process ID. I'm process 1. I'm asking for a user named Tim. And that process ID is going to follow Tim throughout the life of that record of that user. So it doesn't always show up on the slide, but that is Tim1 forever. Now, I still think my username is Tim, but that little bit of metadata is hanging around there. Process 2 asks for a Tim, produces that message to a Kafka topic, to the same topic. Now, they are serialized. They are, by definition, serialized in this topic. If anybody is wondering about partitioning, what if this topic is partitioned? As long as it's partitioned by username, my friend, they are serialized, and we just don't need to worry. So there they are. Those 2 processes have produced their request. We don't know what order they landed in from the outside. I mean, we have this sort of godlike perspective, this omniscient perspective on things, but nobody else knows what's in that topic yet. They just know they asked for a user named Tim. If you look over here, that drum isn't necessarily a relational database. It might be, but it might just be a Kafka Streams K-table. And this is a Streams application consuming these messages. And it's got this in this table. Think of it as a table in memory in a way that's partitionable and scalable. It's got our current users in it. When I consume a message, we'll consume the Tim message. We say, oh, I don't have a Tim. I can add that to the table. Good enough. Now, like I said, that Tim1 follows Tim for his whole life. All right, so there's metadata in there that says I'm Tim1. We'll see why that has to happen in a minute. We consume another request for a username or claim on a username, and we already have a Tim. So sorry, no dice. And we can honestly just drop it on the floor. What we're going to do is we're going to say, sorry, it didn't work. I have nowhere to return a failure indication to. Like, who would I tell? How do I know? I have no name resolution system where I can go route to process 2 and call process 2. Process 2 might be a mobile app somewhere and completely inaccessible to me. So I do not tell process 2 it failed. I just say, I already have a Tim. I'm sorry, store's closed. Now, this application, remember I said before, a stream processing application might have some other life. Like it might also be a Spring Boot application or have some REST interfaces bristling with little REST endpoints all over the place. This one does. And those processes can ask. They can ask, did my Tim get created? And by the way, they're going to send their process ID with that. So it's not just really, is there any Tim, but it's, is there my Tim?
Would you mind taking a question, Tim?
Not at all.
Or a couple, actually.
As long as it's about this.
Yes. Prashanath asks, can I query for events using CaseEqual from one timestamp to another and also apply a filter on the values?
So you can use row time, but I want to say, and I want to say probably not like you're thinking with a time field in a relational database and like get all those records back. You can get a particular one, but you can't do like from here to there. Next question.
Okay, and this is coming from Zach. And Zach asks, is CaseEqual DB a database?
Thank you, Zach. I did say I want somebody to ask that question. I'm going to push that to the end. I want to finish this. There's a little bit more to say, but let me, Zach. I'm gonna come back to your question. Don't you worry.
All right, I'll come back to that one then. And Manjo asks, what are some scenarios that a topic's offset can be lost?
Topic's offset can be lost. I am not sure what you mean. So messages have an offset. When you produce a message to a topic, it gets a monotonically increasing 64-bit integer offset. So topics don't really have an offset, but messages do. And a consumer keeps track of the offset in each partition that it's consuming, that it has assigned to it. And consumers track those locally, remember those locally, and they also persist them to an internal topic in the Kafka cluster. So if you went to a topic, to a Kafka cluster, and you used an admin tool to delete the consumer offsets topic, then you could lose consumer offsets. Your consumers could get very confused, but that'd be a bad thing to do.
Okay, and questions keep rolling in. We've got one more. How can I query for a particular event, and what would we query with?
The thing that you query with is key. Okay, so in CaseEqual DB and in Kafka Streams, you can do an efficient lookup by the key. You can always consume by offset. So if you happen to know the offset of a message, you can always get it efficiently. That's a little bit of an implementation detail, like you don't normally know that. But you can always get the next message with a given key. You can turn keys into tables, as I described. So if you want the current state of an event stream, that table represents the current state of an event stream. But the only way to get a particular event, a particular message, is to know its offset and its partition. And if you just listen to me talking there, that's an awful lot of implementation detail that you need to know, right? Which tells you that that's not quite like, when you think of a database, obviously, well, I want to get at a particular row, and I can pick any key I want. As long as I build an index, I'll get that row in a performant way if the key is unique. Or I'll get a group of rows, and that's what you do. In stream processing, you usually don't do that, right? What you do is you write functions that run over event streams. You're not usually thinking, here is this one event, and I want to get this one event. Instead, you're doing computation over that event stream in this functional way, producing a new event stream as output, or producing a new table as output. And when you're producing a table, that table is the summary of the current state of that event stream. That is the queryable thing. So a stream, you don't really want to think of that as a thing that you query. A stream is a thing you process. You write a function, that function runs over the stream. A table is a thing that you query. And so when you aggregate a table or turn that table into that summary of the current state, then you query that table.
Excellent. And here we've got another one. Add. All right. Would you still be able to look up historical events as a consumer or through KSQL?
Yes, 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 always. So keep it in mind that CaseEqual queries and consumers are functional things, right? A CaseEqual query is this declarative statement that says, take the stuff in this stream and do these computations on it. A consumer is a function that says, send me messages or events in this stream, and I'm going to do this work on them and put my results wherever. That's up to you in a consumer. When you write a new query, a new KaseEqual DB query, or a new consumer, you get to tell that query or tell that consumer whether to start with the next most recent message or the beginning of the topic. So if I want to write a new stream processor that computes all the state and generates some new roll up of that state that I hadn't previously thought of, then I can tell that consumer to start at the beginning. I can also seek to a known offset, right? Like if I happen to know last Monday morning, I save these every once in a while. Last Monday morning was offset 1,048,577. I'll just seek to that and start my processing there. You can do that. It's a little strange. I mean, it's not strange in a bad way. That's less typical. Usually you start at the beginning, you start at the end.
Perfect. That looks like that is it for now.
Awesome. Now, where were we? Okay, this application that's keeping this table of users, and that table could be a relational database, could be a K table. Like implementation doesn't matter here, but it has some endpoint where these processes can ask it, "Is my Tim there? Do you have Tim 1? Do you have Tim 2?" And it will answer. It'll say, "Hey, look, I have Tim 1." So process 2 will know, "Oh, that was Tim 1. That's not the one I wanted." Process 1 will go, "Oh, good. Process Tim, you created Tim 1. I can turn the little box green that says that username is available," or whatever it is I do to get back to the user. Now, notice what's happening here. On the back end, everything is asynchronous. And I'm not really showing how like services can interact with each other. Jason, invite me back later in the year and I'll give that talk. But there's a really neat story about how to integrate microservices through events using Kafka. And that whole back end is entirely event-driven, call it reactive if you want, entirely asynchronous. But like people are not. Well, it's complicated. But when I'm doing something on my phone, I'm saying like, hey, I want to create a new account. I'm typing in TL Berglund. I want to know right away. I'm synchronous. I'm waiting here looking at the thing. And so my synchronous life has to get bridged to this asynchronous back end. And that happens through this RESTful interface where that front end effectively polls or does some efficient way of opening that request and leaving it open to get an answer for when that thing finally exists. I'll leave that there. Consistency. Remember, this was the property of the system where it enforces invariants. There are certain invariants that it will make sure are true, and we just saw that happen. We saw through our isolation solution that automatically gave us unique usernames, and we could work through other kinds of invariants and find similar solutions to them. When you start putting these concurrent requests into a Kafka topic, then we've got one thread that single thread in that stream processing application that's consuming the single partition that we're interested in of that username claim topic. That one thread gets to make an authoritative decision about what's going to be true about the data. So it gets to enforce invariance. So consistency happens. You're able to make consistency happen as a byproduct of the isolation example or the isolation solution. Well, is CaseEqual DB a database, Sean? I appreciate your question. It was Sean, right?
I believe so. Let me go back and find it.
Well, let's just go with Sean. If your name wasn't Sean, it is now. And this is the bummer of not being able to see your faces. All right.
Oh, no, it was Zach.
Zach. My son is named Zach. How could I? Anyway, sorry, Zach. Sean, I know you'd ask a couple questions. I appreciate you. I also appreciate you, Zach. And I just don't know if CaseEqual DB is a database. I want to ask you What is a database anyway? Let's go back to that question. Well, let's think about onions, since I'm sort of priming you with this picture of an onion. What's on the outside layer of a database? Answer that question in your mind right now. I don't know what you said. I say the API is there, and that's SQL. Fine, there's some plumbing, some way of throwing SQL at the database and getting results back. But conceptually, that outer layer is this database, this universal database API that we know and love, called the structured query language. If you peel that layer away, and this is the outer papery layer of the onion, so no one's crying yet, you get a data model. You get tables, right? Tables are awesome. They're strongly typed. You can build indexes on them. You can define constraints. There are cool ways of adding to them and deleting from them and changing them. And when you start thinking about how does all that work, you peel the table layer away. And this is the part of the onion where you definitely are crying. What do you get? You get a storage engine. And if you've ever gone there in a database, this is like pages on disk that are used for update in place changes, the whole read, modify, write thing that you have to do when you're running updates. And all kinds of complex ways of managing those with interacting with the file system in whatever way the database chooses to do that. Super interesting DBA stuff. If you've ever had to go deep on a database, and you probably remember the crying that you did, just like peeling an onion this deep. My question for you, though, is what is underneath that? And this is actually, I'm talking about relational databases. This is true of any database. The Tootsie Roll center of the Tootsie Pop is a commit log. It is a commit log. That's what happens. So in a sense, if you'll allow me, it's like there's this event stream. And when I mutate the database, I am producing a record to this event stream. And all those tables that are in the database, like actually just consuming an event stream, reading a commit log would be terrible. That'd be like if all I ever gave you was a topic and you could read to it and write to it. And I want to know what the current state of the thermostat at Tim's house is. Well, get started at the beginning and read through all of the messages until you've read them all, and then you'll know. That'd be awful, right? Nobody ever use that. So to be useful, databases consume this commit log internally, and it's like they build up these materialized views. Now, materialized view is a thing in most relational databases, but you could think of tables as being, as it were, materialized views of this internal event stream. And so we take that event stream, we build up useful views of it that you actually want to read, that conform to some data model, that can satisfy a performance contract that we want to make, that do all of the things that the database does. We build tables to do that, but they're always derived from the stream of mutations. Likewise, in this kind of what we've been doing with Kafka, if topics become the system of record of this stream of events that have happened, and each service that consumes data from a topic builds up a materialized view, like the user service that we just looked at. Its view is, did my user get created? You don't have to know about the history. You're just asking. I want Tim 2. Did Tim 2 get? Oh, no, Tim 1 got created. I'm so sorry. I'll have to turn my box red and tell my user to pick a different name. Those services are doing that same thing that tables in a relational database are. They're consuming a commit log and building up a useful, interesting, performant, materialized view that satisfies other actors in the system and conforms to the data model that you've advertised and your performance contract that you have committed to. So is CaseEqual DB a database? If it's a database, it's a database with lots of asterisks after database. So if you put it next to Postgres, you're just not going to look at these two things and say, yeah, no, that's definitely the same thing, right? You won't say that. And you're going to need things like Postgres in your life. You need those databases. But databases, as such, specialize in kind of point lookups. It's almost like they're good for that user interface kind of thing. Is there a Tim? Go look in the database for that key and get me that key. But when you're trying to build services that are talking to other services, right? Not software interacting with humans, but software interacting with software, it tends to be more sensible to do that in an event-driven way. And the databases that we've grown up with and that we have made so functional over the last 4 decades, those end up not looking properly fit for that event streaming function. And so that's the role that CaseEqual DB is trying to fill. I mean, it describes itself as an event streaming database. It's not trying to be a special version of Postgres. It really is trying to be a separate kind of thing, strictly for stream processing and for solving the problems that arise around stream processing. Stream processing is the thing you want to do when you have to do real-time analysis of an event stream, or when you've got software that's talking to other software. Doing that in an event-driven way is the sensible thing to do. When you've got humans that are talking to software, well, now I need tables. I'm always going to need tables to look up. It seems like people always want to know, what's the thing? Show me the thing. That's what user interfaces, I mean, that's what CRUD does, right? And so relational databases tend to be very good at that CRUD story. There are, in the margins, there are things you can do with CaseEqual DB that you could also have done with a relational database. If you were using a database table as truly a degenerate key value store, you weren't doing anything more interesting than that, then that's, I'm defining that as a marginal use of a relational database. And in that marginal use, you could have CaseEqual DB kind of expanding, its blob of the architecture and sucking in those few tables into itself. So in the margins, they compete like that, but in any non-marginal use of a table by a relational database, you're not going to say, oh, hey, let me put that into CaseEqual DB as quickly as I can. You're going to keep that around. Now, ideally, that database, that Postgres instance, that MySQL, whatever it is, SQLite, Oracle even, becomes really a materialized view of data in topics. So that event stream is your system of record. And anytime you need to rebuild that database or build a new copy of it or change the schema, make it new service needs a slightly different view of the data, that's fine. You can consume that history and materialize that view. So the state is a computed thing. That state in that relational database, you compute from the event history. You don't use that database as the system of record. In a purely event-driven system, you wouldn't. So is CaseEqual DB a database? Yes, it's this special class of database called a streaming database, and that is so different from what you recognize as a database that you want to make sure you look at it as a thing that is almost never going to compete. You are almost never going to take stuff that's in Oracle and put it into CaseEqual. There are new things that you're doing with event streams that would have been a big pain in the neck with Oracle that are as natural as breathing with CaseEqual. And they are databasey things, but they're just different. So I hope that's I took 10 minutes to answer that question. I always want to be careful with that, because if you ever hear me saying it's a general purpose database throughout your MySQL, you have CaseEqual now, you have not heard words that I've said. And that would be bad advice. But it is awfully database looking, and more so with every version. So to summarize, when you're building services that interact through events, you really are building a giant database. So Kafka itself is kind of like this database construction toolkit. And CaseEqual DB is a sophisticated API on top of that rolls up a lot of difficult stream processing stuff that you would have had to build into that inside-out database. That's really what you're building. And it's an inside-out database that can have ACID semantics if you want. That's pretty cool. Hey, if you want to know more, take a picture of that QR code. It's a great website. There are executable tutorials there. There are videos. Some of those videos have me in them. There's a podcast. Podcast also has me in it. Boy, this sounds like a shameless plug for me. But it's not all me stuff. It's a really great educational site, getting better all the time. More questions, please. And I'd love to stop sharing my screen. Here we are. Stop sharing.
All right, so we've got Tim up on the big screen right now. This is coming from Nick. And Nick asks, would you mind briefly comparing Kafka to AWS Kinesis? At a high level, they seem very similar.
Yes, definitely. At a high level, they do. Um, you aren't going to get long retention periods in Kinesis. And Kinesis is an AWS only thing. So if you sort of like asked Amazon into your heart, uh, it's cool. If you want the ability to go between clouds, then Kafka would be a thing that would give you that. Like you could run Kafka on your own in Amazon. You can run Kafka in Amazon's hosted Kafka. You could run Confluent Cloud, which is multi-cloud. You could run Kafka in Azure, whatever. So you get kind of the open source API and ecosystem. Um, and in Kinesis, you don't get that. Also, kind of the platform stuff like Connect, uh, Streams, you get those things in Kinesis, but again, they're Amazon only, and so you're coding directly to Amazon APIs. If lock-in is that kind of lock-in is okay for you, it might work. The typical, and this is like somebody asked, does Kafka perform well? And I'm about to kind of give general performance answers like that. When I talk to people who build stuff and they do it with Kinesis and they do it with Kafka, there are generally performance complaints that come with Kinesis, which in the cloud come in the form of money, right? To get to big numbers, there's a money curve that is shaped the wrong way. That if you had, say, self-hosted Kafka on EC2 instances, you would have spent less money.
Very good.
Oli, thank you.
Yep, you saw that. Let's see. And we've got a couple more so far. So let's take this one down here. Would you ever recommend MQ over Kafka? And if so, what would the use case be?
Got it. It's difficult for me to imagine, but there is like actual queuing behavior where when you produce a message and then somebody consumes it, it goes away. Like you can only consume it once and it's gone. If you need that guarantee, then you need a queue, and Kafka's not a queue. I think there are some KIPs under discussion that might give it the option for queuing semantics, but it's not a feature in the product right now. So if what you need is a queue and not a log, then yes, use the message queue of your choice. If you are integrating microservices or just doing general data integration or real-time ETL types of things, then message queues are probably the wrong technology. They were right for a lot of things at the time, and they are still right for some things. I mean, most notably, like if it's getting the job done and you have an existing operational commitment to it and you don't feel any pain, then it's the right thing, right? Don't change that. Go do something else that's useful. Even if you'd like to use Kafka, it's not time yet. But for any new work, generally the architectural properties of having events stored in a log give you more flexibility and a more evolvable system than a queue because you have a history.
All right, very good. Let's see. Well, so there's a hypothetical here. Let's say a power outage restarts all the brokers right before a producer produces a message, but before it's streamed to consumers. How would consumers react?
Well, it's not streamed to consumers. So if it's produced and acknowledged, and there's a bunch of little knobs I'm not going to talk about that determine what acknowledged means. That's a very configurable concept. You get to trade off latency and availability there. But it's produced and acknowledged, and the producer says, "Okay, I'm good," and goes on its merry way. It does not get streamed to consumers. The consumers ask for it. So it's sitting there in the log. It's been produced. It's good. And in fact, take you one step further, the follower replicas have to replicate it. And once they've replicated it, it becomes readable by a consumer. So power can go out if it's written to the leader. Then the power can come back up and the followers will say, "Oh, hey, I have a new message that was written to the leader. Let me replicate that to myself." And then it will become readable by consumers. A week later, if I stand up a new consumer, I can still read that message. So Kafka brokers are intentionally dumb. And so they don't want to keep a lot of state. And so they don't know who's consuming from them. So they don't want to push any of those messages out.
Excellent. Very good. I don't see any other questions, but if people get those in real quick, we'll cover those. I don't have anything more at this time unless more questions come up.
Well, I have
I mean,
the
I've got
wish
door prizes, but we'll do that later.
that everybody have a really good night. Thanks for sticking with me and being here. And Utah Jug, thanks for inviting me.
Here we go. I was kind of waiting for this one. All right, so this is from Scott Hastings. He says, a bit off topic, but what is your webcam setup? The video quality is awesome.
Well, where can I include a link? Can I just put a link in chat?
Sure.
I am getting a link from my YouTube channel here. A couple months ago, I made it's an 8-minute video making the most of your home office video setup. Check it out. Basically, I give you kind of 3 stages of ways to optimize your video setup, and mine is the last stage. And I explicitly tell you, you do not want this life. Don't start down this path. It'll cost you thousands of dollars. And yes, you'll be happy, but you'll be broken. So don't do it. Short answer, it's a
That all
Black
sounds
Magic.
about right. Yeah.
Right. It's a Blackmagic Pocket Cinema Camera 4K with the Voigtlander Micro Four Thirds, of course, Voigtlander f.95 17.5 millimeter lens. And I got a softbox over here bouncing off the wall and a little light illuminating my shoulder, a nice little blue splash back there. So it's ridiculously complex, but I love it. Best thing you can do is face an open window. Use your laptop webcam and face an open window, and you'll look great.
Nope. Let's see. We've got another one here. So would an active consumer, quote, reading, unquote, through the power outage automatically read streams after the brokers come back up?
So this is a consumer whose power didn't go out, but the clusters did. So yeah, that consumer is going to time out, right? It loses its connection. The way that works is consumers read messages, and those messages have an offset, and so there's a certain offset that the consumer has read, and then every so often, based on various configurable criteria, say some tens of milliseconds, the consumer will write to a special that consumer offsets topic in the cluster. It'll say, "Hey, I'm at offset 16,777,216 right now," and it'll write that to that consumer offsets topic. And so if that consumer dies right then and comes back up, when it comes back up, it says, "Oh, hey, by cluster, by the way, I'm consumer so-and-so. Do you have an offset for me?" And it'll say, "Oh, yeah, we do. You have these partitions. And in partition 3, you were at 16,777,216. It says, "Oh, thank you." And it'll start consuming from there. So the cluster remembers consumer offsets. The consumer can have read ahead and not synced its consumer offset, which means it would reprocess those messages from its last consumer offset. So whatever those were. If you want to guarantee that you process messages exactly one time, there's a transaction API that you can use in the consumer and the producer. So that's a producer to consumer kind of flow. It's not hard. There's not a lot of code that you have to write. But that exactly once API kind of gets you out of that double processing thing. At Kafka Streams and CaseEqual, we'll use that automatically as the configuration switch. You say, "Give me exactly once," and it gives you exactly once.
Very good. All right, I'm going to go over the few door prizes that we've got, and then, unless there's questions that come up during that, I think we will call it a night.
Excellent.
So let me share real quick. All right, so we'll share that, and Tim goes, oh, maybe. I'm going to mute Tim. And door prizes. All right, here we go. So the two JetBrains licenses are going out to Prashanath Bachu and Rebecca Hall. Let us know which IDE you're interested in, and we'll send you out the code for that. And then the last one, so the Agile Learner from Venkat, the 1-year subscription to his website goes out to Jennifer Baxter. And Jennifer, I will send that out to you, and you should get that later on tonight, and that should do it for the screen share, or not the screen share, but the door prizes. Going back through real quick, once again, upcoming schedule next month on the 9th, so you'll note the date change on that. We have Daniel Hinojosa talking about Java generics. Back in August, possibly back at LucidWorks, although I'm not going to hold my breath. We have Mark Richards, and in September we have Nathaniel Shuda talking about thinking architecturally. And I believe that should do it for those of us here. Once again, thanks everyone for being here. Appreciate everyone coming, and we look forward to seeing you again next month. Thank you. So there's a question here, where can we look for the URL to reconsume this presentation? You can come back here to this URL right here, and it will work here. And then there's also, if you scroll through the chat, there's YouTube links as well. So we've got that. Once again, thank you everyone, and we hope you all have a great month. Thanks.